you are all doing well. My name is Dr. Amar Kumar De, and I am excited to welcome you to today's lecture titled Phase Modulation Technique, Equation and Bandwidth for the course Fundamental of Communication System and its Application. It's exciting to see you, so many of you joining us from different corners of the world. First and foremost, I want to extend a warm thanks for taking time to be a part of this session. So, without further delay, let's move on to the topic titled Phase Modulation Technique, Equation and Bandwidth. Before moving ahead, here's a quick overview of today's lecture titled Phase Modulation Technique, Equation and Bandwidth. Today, we are going to dive into the fascinating world of phase modulation, which is an essential concept in communication system. We will cover basic concepts of phase modulation, which involves varying the phase of the carrier wave in accordance with the input signal. Then we delve into the mathematical representation. Then we will discuss the bandwidth requirement for phase modulation. Bandwidth is a crucial aspect of any communication system. This highlights the practical implementation of bandwidth considerations and demonstrate how phase modulation can achieve high bandwidth efficiency. Then we look into the practical implementation of a phase modulator in the topic block diagrams of phase modulator. Once we get an overview of phase modulator, we will approach for the phase demodulator. And finally, I will conclude this lecture session with a brief summary. Now, let us start with the detailed coverage of the content. First of all, we start with the importance of modulation. Understanding the phase modulation is crucial because it provides a robust method for transmitting data with high fidelity. Phase modulation is particularly significant in digital communication system, where accuracy and efficiency in data transmission are very important. It's find widespread use in applications such as digital synthesizer, modems, and advanced communication system. By mastering a phase modulation technique, we can improve the reliability and quality of data we transmit, making it a cornerstone of modern communication technologies. Exploring the significance of phase modulation in communication, let's explore why phase modulation holds such a significance in the field of communication. Phase modulation, abbreviated as PM, is a cornerstone of modern communication system. Its robust, high fidelity, efficient bandwidth uses and wide range of application made it essential for various communication technologies. Now, in terms of robust data transmission, phase modulation provides a highly robust method for transmitting data by varying the phase of the carrier signal according to the input signal amplitude. Phase modulation ensures that the information is encoded in a manner that is less susceptible to noise and interferences compared to the amplitude modulation. This robustness makes phase modulation ideal for environment where signal integrity is important, such as in wireless communication systems and satellite link. Next is high fidelity and accuracy. Moreover, phase modulation is particularly valued for its ability to transmit data with a high fidelity and accuracy. In digital communication system, whenever minor errors led to a significant data loss or corruption, phase modulation ensure precise and reliable transmission of digital signals. This capability is critical for applications like digital audio and video broadcasting, data communication, and high-speed internet services. Efficient use of bandwidth. Furthermore, one of the key advantages of phase modulation is its efficient use of bandwidth. Unlike frequency modulation, FM, we can require a wide bandwidth. Phase modulation achieves this high data rate within a relatively narrow bandwidth. This efficiency is vital in modern communication networks where the demand for bandwidth is constantly increasing. it allows more channel to be accommodated within a given frequency spectrum, thereby enhancing the overall capacity of the communication system. Applications in communication systems are phase modulation find extensive used in advanced communication system. For instance, in digital synthesizer, phase modulation is utilized to generate a wide range of sounds and effects. In modems, PM modulates digital data for transmission over telephone line or other communication media. Moreover, PM serves are fundamental concepts in many of modern modulation schemes such as quadrature amplitude modulation and quadrature phase shift keying, which are integral to high-speed data communication network including Wi-Fi, LTE and 5G. One of the important significance of phase modulation is enhanced signal integrity. Phase modulation significantly enhances signal integrity over long distances due to its modulation of signal phase. Phase modulation is less affected by amplitude variations resulting from signal fading or multipath propagation. These key features make phase modulation particularly effective in wireless communication system where maintaining signal integrity is challenging environmental condition is crucial. The future prospects and research. Continuous research in phase modulation explores new avenues to enhance efficiency and application. Innovations in phase modulation technique promise to further improve data transmission rate, reduce power consumptions, and enhance overall communication system performance. Engineers and researchers staying informed about this development can leverage phase modulation to push the boundaries of communication technologies possibly. So, in summary, phase modulation is a cornerstone of modern communication system due to its robustness, high fidelity, efficient bandwidth usage, and wide range of applications. Its significant and future potential make it an essential area of study for anyone looking to excel in the field of communication engineering. Now, let us move to the next section, the mathematical representation of phase modulation. In this section, we will delve into the mathematical representation of phase modulation. Understanding the mathematical foundations of phase modulation is essential for comprehending how these modulation techniques operate on a theoretical level. We will cover the key formulas and equations that describe PM, providing you a deeper insights into its functionality and applications. Now, let's begin with the basic concepts. In phase modulation, the phase of the carrier wave is varied in accordance with the amplitude of the input signal. Mathematically, this relation can be expressed using a few key equations. The carrier signal in phase modulation is typically represented as C of t is equal to AC cos omega Ct plus phi of t, where AC is the amplitude of the carrier, omega c is the angular frequency of the carrier, and phi of t is the phase modulation function which varies with time. The phase modulation function phi of t is directly influenced by the input or message signal m of t. The general form of phase modulation function is phi of t is equal to Kp into m of t, where Kp is the phase sensitivity constant determining how much of the phase of the carrier signal varies in response to changes in the message signal. Mt is the message signal or the modulating signal. Substituting phi of t into the carrier signal equation, the phase modulated signal equation becomes S of t is equal to AC cos omega Ct plus Kp m of t. This equation illustrates how the phase of the carrier wave is altered by the amplitude of the message signal m of t. To gain a deeper understanding, it is important to consider the concepts of instantaneous phase and instantaneous frequency. The instantaneous phase theta of t of the modulated signal is given by theta t is equal to omega c plus Kp into m of t. The instantaneous frequency Fit can be derived from the derivation of instantaneous phase with respect to time. So, f of t is equal to 1 upon 2 pi d theta of t by dt, which is equal to omega c by 2 pi plus kp d of mt dt by 2 pi. This equation shows that the instantaneous frequency is combination of carrier frequency omega c upon 2 pi and the derivative of the message signal m of t. Now, the bandwidth of the phase modulated signal is an important aspect to consider. While we discuss the bandwidth requirement in detail later, it's worth noting here that the bandwidth of the PM is influenced by the frequency range of the message signal and the phase sensitivity constant Kp. Carson rule, which we will derive and explain in this subsequent section, will provide a practical method for estimating the bandwidth of PM signals. To fully grasp the behavior of PM signal, spectral analysis using Fourier transform is often employed. The Fourier transform of the phase modulated signal S of t helps in understanding the frequency component and spectral density of the signal. This analysis is crucial for designing and optimizing communication system that uses phase modulation. By understanding this mathematical representation, we gain a deeper appreciations of how phase modulation works. This theoretical foundation not only aids in the designing and analysis of phase modulation system, but also help in troubleshooting and improving existing communication technologies. In the next section, we will explore the bandwidth requirement of phase modulated signal in more detail, building on the mathematical concept we just covered. So, the bandwidth requirement of phase modulation. In any communication system, the bandwidth is crucial factor for determining the system capacity to transmit information efficiently. So, the importance of bandwidth is crucial because it directly impacts the quality and reliability of communication. Signal with insufficient bandwidth may suffer from overlap with adjacent signal, leading to interferences and noise. On the other hand, using more bandwidth than necessary can be insufficient and waste valuable frequency spectrum resources. Therefore, finding the right balance of bandwidth allocated is essential. The bandwidth of the PM signal is influenced by several factors, including the frequency range of the message signal, MT, and the phase sensitivity constant, Kp. To understand the bandwidth requirement of PF signal, we need to analyze the signal spectrum characteristic. So, in order to get a deeper concepts of bandwidth, let us go for the Carson rule. One of the most widely used method for estimating the bandwidth of PM signal is the Carson rule. Carson rule provides a practical approximations for bandwidth of angle modulated signal, including FM and PM. According to Carson rule, the approximate bandwidth B of a PM signal is given by B is nearly equal to 2 times del f into FM, where del f is the peak frequency deviation, which is the maximum shift in frequency from the carrier frequency due to modulation. FM is the highest frequency component in the message signal, MT, M of t. Now, let us derive and explain this Carson rule. To derive Carson rule, we first consider the frequency component of the PM signal, where the message signal M of t modulates the phase of the carrier, resulting the signal spectrum consisting of carrier frequency and multiple sidebands. The bandwidth of the PM signal is determined by the range of this sidebands. There is an important term, that is the peak frequency deviation, del f. In PM, the peak frequency deviation is proportional to the maximum rate of change of the message signal. It can be expressed as del f is equal to Kp into del m, where del m is the peak amplitude in the message signal. Next important component is the highest frequency component, FM. The highest frequency component of message signal is crucial factor because it determines how fast the phase of the carrier can changes. Faster change in the message signal leads to a wider frequency range in the modulated signal. Combining these factors, Carson rule approximate the total bandwidth required to estimate the significant spectral component of the PM signal. This approximation ensures that most of the signal power is contained within the calculated bandwidth, reducing the likelihood of interferences with the adjacent channel. In practical communication system, adhering to bandwidth requirement is vital for regulatory compliances and system performance. Communication standards and regulations often specify the maximum allowable bandwidth for different types of modulation to prevent interferences and ensure efficient use of the frequency spectrum. For instance, in radio broadcasting, the allocated bandwidth may be sufficient to accommodate the modulating signal while avoiding overlap with the neighboring channel. In digital communication system, adequate bandwidth ensures that data can be transmitted at a desirable rate without excessive error or signal degradation. The bandwidth efficiency is a very important concept. Bandwidth efficiency refers to the ability to transmit the data within a given bandwidth. PM signal, due to their phase variation nature, can achieve high bandwidth efficiency, making them suitable for various applications, including digital synthesizer, modems, and advanced communication system. By optimizing the phase sensitivity constant Kp and carefully designing the message signal M of t, engineers can maximize the data transmission rate while minimize the required bandwidth. So, I just need to conclude this section. Understanding the bandwidth requirement for phase modulation is essential for designing efficient communication system. By applying Carson rule and analyzing the spectral characteristics of PM signal, engineers can ensure that their system operating in the allocated bandwidth, providing reliability and high quality communication. In the next section, we will explore the various applications of PM and how bandwidth characteristics make them suitable for different use cases. The detailed explanation of bandwidth requirement for PM signal highlights the importance of bandwidth in communication system and provide a clear understanding of how to estimate and manage it for effective data transmission. Now, after completing the mathematical representation, getting the knowledge of the bandwidth requirement, it's time to go for the block diagram of a phase modulator. Phase modulator is generated using a differentiator and a frequency modulator, involving a clear manipulation of relationship between frequency and the phase. Since frequency is the derivatives of phase, we can use our differentiator to convert a phase modulated signal into a frequency modulating signal. Here is a step-by-step explanation of how this can be achieved. First, the input modulating signal. The modulating signal, the initial step is to provide the baseband signal which contain the information to be transmitted. This signal is typically an analog waveform. The second is differentiator. The purpose is a differentiator circuit is used to differentiate the input modulating signal. This step is crucial because the frequency deviation in frequency modulation signal is proportional to the derivative of the phase of the modulating signal. Now, the differentiator takes the phase modulating signals which would normally be used to modulate the phase of the carrier directly and outputs its derivative. This effectively converting the phase modulation into frequency modulation. The frequency modulator. The purpose of the frequency modulator is to generate the frequency modulated signal based on the differentiated output from the differentiator. The output of the differentiator is used as the input to the frequency modulator. The frequency modulator then varies the frequency of the carrier signal according to the differentiated signal. This input signal is the derivative of the original phase modulating signal, the resulting FM signal corresponding to the original phase modulation. Below is a simplified diagram to visualize this process. The modulating signal provides the baseband signal that contain the information to be transmitted. The signal modulates the phase of the carrier in the traditional PM. The differentiator converts the phase modulating signal into frequency modulating signal. The differentiator output a signal whose amplitude is proportional to the rate of change derivative of the input signal. If the input signal represents the phase, the output represents the frequency. The frequency modulator modulates the frequency of the carrier signal according to the inputs of the differentiator. The frequency of the carrier is varied in direct proportional to the input signal from the differentiator. This creates a frequency modulated signal that reflects the original phase modulation information. By using this differentiator, the phase modulation signal is transformed into this frequency modulated signal. This frequency modulated signal is then fed into a frequency modulator, which produce the frequency modulated carrier wave, because the frequency derivatives of FM signal correspond to the derivatives of phase of the original modulating signal. This method is effective in generating the phase modulated signal. By following these steps and understanding the underlying principle, phase modulation can be effectively generated using differentiator and a frequency modulator. Now, once we have an understanding of modulation, it's time to go for the demodulation process. A phase demodulator is a device or a circuit that extracts the original information signal from the phase modulated carrier. The primary component of the phase demodulator works together to convert the phase variations of the received signal back into the original modulating signal. Here is the explanation for the block diagram and the functions of the phase demodulator. In this, we are going to see the principle of the phase demodulation process. There is a very important component in phase demodulation, that is a PLL based phase demodulator followed by an integrator is a sophisticated method used to demodulate the phase modulated signal. This method is widely used to lock on the phase of the incoming signal and then use an integrator to recover the original modulating signal. A PLL is a feedback control system that synchronizes the phase of the generated signal with the phase of the incoming signal. A typically PLL consists of the following component: a phase detector. Compare the phase of the incoming signal with the phase of the output signal from the voltage controlled oscillator. Low pass filter. The filter the output of the phase detector to remove high frequency component. Voltage controlled oscillator generates an output signal whose frequency is controlled by the input voltage from the filtered output of the phase detector. Loop filter, additionally filtering to control the dynamics of the loop and usually integrate within the low pass filter. The principle of PLL based phase demodulator is the phase detector compare the phase of the incoming phase modulator signal with the phase of the signal generated by VCO. It provides an error signal proportional to the phase difference between the input signal and the VCO output. Now, the output is given to a low pass filter. The function of the low pass filter is to smoothen the error signal from the phase detector by removing the high frequency noises and retaining the low frequency phase difference signal. A DC signal or a low frequency signal proportional to the average phase difference is produced. The voltage controlled oscillator adjusts its frequency and thus its phase based on the input voltage of the low pass filter. A signal whose phase is logged to the phase of the incoming signal is produced at the output. Now, if you try to understand the demodulation process, in this demodulation process, the input to the input is the modulating signal, which is S of t is equal to AC cos omega ct plus phi of t. The input to the PLL is a phase modulated signal where phi of t represents the phase derivation proportional to the modulating signal m of t. The phase detector compares the phase of the input signal with the VCO output and produces an error signal proportional to the difference, where VPD of t is proportional to del phi of t. Here, del phi of t is the phase difference between input signal and the VCO output. Then, the low pass filter the error signal yields a signal proportional to the phase derivative. That is, the V low pass of t is nearly proportional to phi of t. The signal is a low frequency representation of the phase derivative. The voltage controlled oscillator adjusts its phase to match the phase of the input signal based on this filter error signal. Now, the integrator, after obtaining the phase derivative signal phi of t from the PLL, the next step is to recover the original modulating signal m of t. Since phi of t is proportional to the integral of modulating signal m of t, we need to pass this signal through an integrator to recover the m of t. So, in short, in summary, the input phase modulated signal, the input PM signal consists of the modulated phase information, the PLL demodulator, the phase detector in the PLL produces an error signal based on the phase difference between the input signal and the VCO output. The low pass filter smoothens this error signal, provides a signal proportional to the phase derivative phi of t. The VCO adjusts its phase to match the incoming signal, effectively tracking the phase of the input signal. The output from an PLL low pass filter is passed through an integrator. The integrator recovers the original modulating signal m of t by performing the differentiation operation on phi of t. By utilizing a PLL followed by an integrator, we can effectively demodulate phase modulated signal and retrieves the original modulating information with high accuracy and fidelity. Understanding the block diagram and the role of each component in the phase demodulator is essential for analyzing and designing the system that effectively recovers the original information from phase modulated signal. So, with this we have come to an end to today's lecture. Thank you for your attention. Before we conclude, I would like to take a moment to thank all of you for your participation and attention throughout this lecture. Take care and have a great day.